Hi, I'm Daniel Chan from UNSW Sydney. This is video 5 in my short course on points at topology. And in this video, I wanted to introduce the very important condition on topological spaces called the Hausdorff condition, which allows the notion of limits to be well behaved, that is, to behave like we see them in calculus. Okay, so let's start with our terminologies and our notation. X is always going to be a topological space. And what does it mean for this topological space to be Hausdorff, or another way of stating that is it's a T2 space. Okay, so the condition is as follows. What we do is we look at every pair of disjoint points x1, x2 in our space X. So here like this, x1, x2. And we want to say that given such a pair of distinct points, there are open neighborhoods of each of them, Vi, so V1 and V2, open neighborhoods of x1 and x2, such that their intersection is empty. So the situation that you should find here is something like this. Here are 2 points. You can find an open neighborhood, like this one here, V1 here, and another one like this, V2, and their intersection is empty, so they're disjoint. So this condition here, the existence of these open neighborhoods which are disjoint, is an example of a separation axiom. Okay, so you want this for each and every pair of distinct points, x1, x2, and here you can separate the points by actual open neighborhoods in this sense. Okay, so that's the definition, and let's look at some examples. And the first thing to note is that any subset of Rn, remember that has a default Euclidean topology. Rn has a Euclidean topology, and since this is a subset of a topological space, it has the subspace topology, and that's also called the Euclidean topology. And any subset of Rn with the Euclidean topology is Hausdorff. So why is that true? Okay, so remember inside Rn, where does the topology comes from? In this case, we have a notion of distance and a metric. So given any 2 distinct points, x1, x2, there's a distance between that, and that distance is strictly positive. Okay, so what we can do is we can look at that distance and we can halve it. And if we pick any epsilon ball about x1 and x2, which is less than half that distance, so maybe the midpoint is here, as long as that epsilon ball is such that epsilon is at most half the distance between them, those 2 open sets will be disjoint by the triangle inequality, essentially. Okay, so there are 2 open neighborhoods of those points whose intersection is empty, and since you can do this for any pair of distinct points inside X, this is going to be a Hausdorff space. Okay, let's look at another example which is not Hausdorff now, and this is rather interesting, and we're going to get it from an example which is Hausdorff. Okay, we start with basically a pair of lines. Okay, and let's be specific. We'll situate the 2 pair of lines inside the plane R2 with coordinates x and y. Okay, so maybe you have the y equals 0 line here and the y equals 1 line here. Okay, so it's a subspace of this space here, so it has the default Euclidean topology. Okay, and it's very easy to see what are the open sets here. Okay, you just need an open set here and an open set here, and it's the union of something like that. Okay, so they're the open sets inside this Euclidean topology. And what we're going to do is we're going to form a quotient space out of that. Okay, we're going to put an equivalence relation on here. Okay, and then that's going to define a map from this Y to the set of equivalence classes, and then we put the quotient topology on that. So what's the equivalence relation? Well, it's going to be very simple. What we're going to do is we're basically going to zip up these 2 lines to be the same everywhere except at 0. So what does that mean? Okay, so we need an equivalence relation here. So basically, I'm going to make alpha 0 here on this y equals 0 line to be equivalent to alpha 1 on this y equals 1 line. So they're going to be identified for which values of alpha for every alpha non-zero. Okay, so alpha 0 is equivalent to alpha 1 as long as alpha is non-zero. So all non-zero alpha. So basically, we zip up these 2 all the way except for at 0. And so one way to think of it is now, since you've zipped them up almost everywhere, we get something very much like a line, but there are 2 zeros, one at y equals 1 and one at y equals 0, that remain two separate points. Okay, so there's a point here and a point here, okay, which correspond to these 2 points. They're no longer, they're not identified, but all the other ones are identified like that. Okay, so I want to claim that this is actually not Hausdorff. So why is that true? To be Hausdorff means that given any 2 distinct points, you can separate them with disjoint open neighborhoods. So let's look at these 2 points. I claim, and hopefully you can see quite clearly, that you can't separate these 2 points using open neighborhoods. Indeed, if you have an open neighborhood of the top point here, okay, of course, that means that the inverse image is going to be open inside here. So basically, you want some open, at least some open interval containing this. So at least you'll have something to the left of this point and to the right of that point. That's an open neighborhood of the top point. Similarly, if you have an open neighborhood of the bottom point, you'll have to have something to the left of this point and something to the right of this point. So of course, the intersection has to be non-empty, okay? It's a non-trivial intersection, so it is not Hausdorff. Okay, so this is a very interesting example. It's quite easy to construct once you understand quotient spaces. And one thing that you should note in this example, which is peculiar, is that suppose you want to travel along this line. You can pick a sequence and do it discretely, or you can do it continuously. When you go towards this x equals 0, you have 2 separate limits. Okay, you have the top one and the bottom one. Okay, because they will correspond. If you move along here, that's the same whether you move along the top or on the bottom. Okay, they've been identified now, and so you can take the limit as either this 0 or this 0. So in this case, it's rather interesting that for this space here, there are cases where you can have sequences where the limit is not unique. Okay, so let me show you the all-important proposition, which is one of the big reasons why we're interested in Hausdorff topologies, and also says that often with our intuition, when we think about topologies, the ones that we understand the best are the ones which are Hausdorff. Okay, so let's look at this proposition. X now is a Hausdorff topological space, and we're going to look at a sequence inside there. Okay, so here's our X, and here we have a sequence inside this X, and let's suppose it has a limit as n goes to infinity of xn. Well, if it has a limit, then I claim that it has to be unique. Okay, so let's see why that's true, and it's quite easy, and it follows quite simply from the separation axiom that we have here. Okay, so suppose instead there are 2 limits. Okay, there's an x and there's an x prime. Okay, so what I want to do is I want to give a contradiction to that. Okay, so I want to do that by contradicting this Hausdorff condition here. Okay, so suppose they're separate limits, so they're distinct. Then firstly, what does it mean to be a limit? Okay, so firstly, it means that if you have any open neighborhood of x, for example, so there's an open neighborhood, maybe that's V, it has to include infinitely many of these elements in the sequence. So all xn will be in there as long as n is bigger than or equal to some sufficiently large big N. Okay, so that's what that means. Okay, so it will contain all but finitely many of this sequence. Okay, also, what does it mean that x prime is a limit of this sequence? The same thing. Okay, so given any open neighborhood of this x prime, okay, let's call it V prime, it has to contain infinitely many of this sequence. Okay, so in fact all but finitely many. But the most important thing is that since both these open neighborhoods contain points of that sequence, okay, infinitely many in fact, the intersection cannot be empty. Okay, so V intersect V prime is non-empty. So in other words, it doesn't matter what open neighborhoods you pick for x and x prime, doesn't matter how small they are, they will always have an intersection which is non-empty because it will contain elements of the sequence. Okay, so since you can't separate these 2 points with open neighborhoods, what that means is that this space cannot be Hausdorff. Okay, and that completes this proposition. So this is a very nice simple condition, okay, a natural condition using the separation axiom, which guarantees uniqueness of limits. This Hausdorff condition is an example of something called a topological property. Okay, so what do I mean by that? So let's start with some class of topological spaces. So it could be the class of all topological spaces, but it could be something smaller. It could be just, for example, metric spaces, if you know what they are, or just even subset of Rn for arbitrary n, where you look at the Euclidean topology. Okay. Now, given such a class of topological spaces, you might have some property associated with them. For example, with metric spaces, you can talk about sets which are closed and bounded. Okay. So, given such a property, we can ask whether it's topological or not. Okay, it's topological if the following condition holds. Okay, so given any homeomorphic x and y that's in this class of topological spaces, then one of them has that property, x has that property, if and only if the other one, y, has that property. Okay, so basically, as far as the property is concerned, okay, homeomorphic ones either both sit in there or they both do not sit in that class with that property. Okay, so in topology, we're really trying to understand topological properties. Okay, so this second proposition states that being Hausdorff is actually a topological property. Okay, so this is a topological property defined on the class of all topological spaces, and let's see why it's true. Okay, so the best reason to understand why it's true is to realize it's because how did we define being Hausdorff? It was defined purely in terms of the data of a topological space. Okay, you just said that given any pair of distinct points, you can separate them with open neighborhoods of each of them. So the only data you need to define that is just using the data of a topological space. Okay, open neighborhoods and also a set theory. Okay, so let's see more precisely why that's true. Okay, so suppose now we have some homeomorphism f from x to y. And we're going to suppose that x is Hausdorff. We're going to show that y is Hausdorff too. And then, of course, since f inverse is also a homeomorphism, that proof will also show that if you assume that y is Hausdorff, then x will be Hausdorff. Okay, so we just need to prove that one implication this way here. Okay, so let's do that. So we've got some space x here and some space y here. You've got some homeomorphism f, and then there's also an f inverse. Okay, and what we want to show is that assuming x is Hausdorff, y is also Hausdorff. So let's check the condition that it's Hausdorff here. We've got two separate points, y and y prime. Okay, so the way to think of this is that you know this one's Hausdorff. Okay, so it satisfies some axioms which are defined in terms of the topology purely. Okay, here, and the thing is that you can transfer the fact that it satisfies it here to the fact that it satisfies it here. Why is that? Because this is a bijection, which not only is it an isomorphism of the sets, it's an isomorphism of the topologies as well. Okay, so we can think of this relation, this identification of these two as basically, well, these two are the same. All I've done is I've just renamed the points of x with points of y by using this f. Okay, so that means checking that this is Hausdorff on this side is the same just by changing the names with checking that it's Hausdorff on the other side. Okay, so let's see explicitly how that works here. Okay, so we want to check that it's Hausdorff, and basically we want to say that if you just change the names back here, you get it's Hausdorff here, and that will show that it's Hausdorff here. So let's see how that works. Okay, so we want to find open neighborhoods of these 2 points. Okay, so let's just pull back everything to the x space. Okay, so this y will correspond to a unique point here. I'll call it little x. Okay, so we'll have some x here like this, and the y prime will correspond to some point x prime here. So it's continuous, so it can stretch, so it could be that they're a lot closer together now, like that. Now, well, you want to use the fact that, okay, so the fact that you have 2 distinct points here, these are bijections, so these are still distinct here. Okay, now you want to use the Hausdorff condition here, right? So that means you can separate these two with open neighborhoods. Let's put in those open neighborhoods. Okay, so maybe they're v and v prime. They're open neighborhoods which are disjoint. Okay, so you've got it's satisfying with checking in this particular pair of disjoint points that you've got this separating pair of open neighborhoods. Okay, and we want to transfer the fact that this axiom, this part of the axiom is satisfied over to here. So all we need to do is we just apply f to the whole diagram. What do we get? So remember, f inverse is continuous. Okay, So that means F, its inverse image, maps opens to opens. Okay, so you can look at the image of V prime, that will give you some open neighborhood of Y prime. It might be a lot bigger, but it will be whatever it is. Okay, it's an open neighborhood. You can look at the image of V, and that will be some open neighborhood of Y. Okay, and the fact that these two are disjoint here means that these two are disjoint over here. So this separating pair of open neighborhoods gets mapped over by this F to a separating pair of open neighborhoods for the points Y prime and Y. And since Y and Y prime were arbitrary distinct points here, that shows you that this Y has to be Hausdorff as well. So this Hausdorff condition is a very interesting topological property, and in our next video we will look at another interesting topological property, that of connectedness.